Good morning, everybody. These are our notes today on Kepler's laws of planetary motion. So these notes will be pretty quick. Then after these notes today, we'll be doing a little review sheet or getting you started on a review sheet for your test on Friday. So what I want you to do is go to your table of contents and you're going to put in Kepler's laws of planetary motion and the page number that you're on. Not sure what page number you're on, and the date. Today is November 13th. So that's what I want you to do right away. Then go to your next page of notes where you left off, and at the top, I want you to put in Kepler's laws of planetary motion. So these notes, like I said, are pretty quick notes. So let me put my clicker here. There we go. So for those notes today, we're going to do Kepler's first law, second law, and third law. So his first law, you want to put in there, Kepler's first law. It's actually called the law of ellipses. And when we were in the hallway last week playing around, we actually did this. So let me pull that up really quick because we're all out there. So this is a video from our third hour class. So let me pull it up. And so you guys can see that. So this was our third period class. This is when we're in the hallway, demonstrate the path of a planet around the sun and the second foci. So the other pole in our hallway was our second focus. So the path that it took was in the shape of an ellipse. So this was a video that we took during third hour. Okay, so I just wanted to remind you, for those that weren't here last Friday, this is what you missed. So let me go back to our notes section. Pull that back up for us. Let me make sure we're recording. There we go. So for the law of ellipses, what you want to do, your first bullet, planets move around the sun in elliptical orbits. All right, so planets move around in the ellipse. Remember, ellipse is just a fancy name, the scientific name for an oval. And the term we use for our ellipses, how elliptical of an orbit was called eccentricity. You guys were calculating this in the hallway last week. It's a measure of how nearly circular the ellipse is. And the formula we used was E for eccentricity equals C divided by A. On the test on Friday, you'll have that formula already. You'll have C and A, and you'll also have eccentricity. You're just going to have to decipher what numbers mean the orbit is more elliptical or more circular. So how do you do that? Very, very simple. So if the eccentricity is 0, so equals 0, perfectly 0, it's going to be a circular orbit. So that path the planet takes around the sun will be circular. No planets do that perfectly, okay? Some are very close, but nobody has a perfect circle. Eccentricity that is greater than 0, the more elliptical the orbit's going to be. So the further a number away from 0 is, the greater the ellipse will be. So the most elliptical planets we have are Mercury, that we know about, around our sun that we know about, are Mercury and Pluto. They have the most eccentric orbits. Okay, so that's what I got going on. Mercury and Pluto orbits are the most eccentric. So if you see over here to the right, the blue line represents the orbit around the sun. So this planet, let's say this planet is Mercury. So you can see this orbit is not circular. It is elliptical, oval. All right. So you have the sun here, the second focus point here. The second focus point, remember, is imaginary, so it's just there for us. So the sun is never in the middle. It's always off to the side in a planet's orbit. So it's off-center. So Kepler's first law, a law of ellipses, planets move around the sun in elliptical orbits. Very easy, right? So you should know that and never, ever forget it. So let's move on. Let me take off my light, brighten it up for us. And there we go. All right, moving on to Kepler's second law. So I'm going to go right here. So Kepler's second law, this is called the law of ellipses. This is called the law of equal areas. All right. And there's a reason it's called the law of equal areas. Uh, Pretty much it describes the speed of a planet traveling around in an elliptical orbit around the sun. And it states that the line between the sun and the planet sweeps equal areas in equal times. So let me highlight what I just read for you. So it describes the speed of the planet. So as our planet, so here's the orbit again. It's a planet's orbit around the sun. Let me bring this up. So here we go. So you have distance x right here in purple, and you have distance y over here, area y over here, distance y. The planet's orbit around the sun. All right, so here's our ellipse. Here's our sun. So pretty much what this law says is planets move distance x and distance y in the same amount of time. So the time it takes to move from here to here is the same amount of time a planet takes to move from here to here. And there's a reason for this. And I'm going to go back over here to the notes. I'll leave my light on. So planets move the fastest when they are closest to the sun. We call this perihelion. So right over here, closer to the sun, the planets moving the fastest. When planets move the slowest, they are farther from the sun, and this is called aphelion. Okay? So, how this works with the law of equal areas. So if the planet is moving really fast over here, it could cover a greater distance. However, if a planet is moving slower at aphelion, it covers less of a distance, but at the same amount of time. All right? So it's moving faster, moving slower, but they cover the same amount of distance. So that's what's meant by the law of equal areas. That a line between the sun and the planet sweeps equal areas in equal times. And this all has to do with the sun's gravitational pull on that planet. So this is Kepler's second law of equal areas. Let me take this off so it's brighter for you guys. So this is what you want to put down for the law of equal areas. So this information right here. And maybe drawing this out to the side of your notes will also help you out as you go along. So again, if you need to pause, if I'm going too fast, please pause so you can get these notes down. I'm going to move on to Kepler's third and final law. So let me scroll down here. All right, we got Kepler's third law, and the third law is pretty cool because you know what it's called? The law of harmonies. All right, so which is pretty cool, I think. So let me bring my cursor back up. I don't know why I can't do anything with my cursor. There we go. Is it going to work? There we go. All right. So Kepler's third law of harmonies. So this one, they give you a nice big formula. We're not going through the formula in our class. For our class, we don't have to go into that. What we need to know for our class is the length of time for a planet to orbit the sun increases rapidly with the increase of the radius of the planet's orbit. So, very simple. The further away from the sun, the longer the orbit of that planet. The longer the orbit of the planet, the longer a Earth year would be on that planet. So, which planet would take the longest time to orbit the sun? So, we have this nice picture right here. So if you're looking over here at this image, oh, it's making it move. I don't want you to move. So we have our picture right there. So which of these planets? We have Mercury, Venus, Earth, Mars, Jupiter, all the way out to Neptune. So which one would take the longest to orbit the sun? Again, the length of the time a planet to orbit the sun increases rapidly with the increase of the radius of the planet's orbit. So if we go out here, whichever planet is the furthest away, Neptune is most likely going to have the longest orbit because its orbit is the furthest away from the sun. All right, which planet would take the shortest time to orbit the sun? Now let's go back here. Closest to the sun would be Mercury. So the law of harmonies, not that hard. It's pretty much telling you the further away the orbit, the longer that takes the planet to orbit sun. So on the test, you would get charts showing you the amount of Earth years it would take to orbit a sun, and you're just going to have to decipher that chart. Also, in this notes with law harmonies, I put AU in here. What is AU? And I don't think we've covered this in class, but you might have seen it on some of your assignments. So what AU represents is astronomical unit. And what that means, it's pretty easy. It's the mean distance between the Earth and our sun. So it's the distance from our Earth right here and the sun. So that distance is approximately 93 million miles. All right. So from our sun to our Earth, 93 million miles. That's a lot, isn't it? So when you see on a chart talking about 2 AU, 3 AU, 4 AU, so they're taking this number, 93 million miles, and multiplying it by 4. All right. So AU is just the distance between our Earth and our sun. So they might say Jupiter is 5 AU. I'm just throwing numbers out there. All right. So this is 5 times 93 million miles. This gives you a perspective of their distance from the sun. So these were our notes for today. I said they're really, really quick. Kepler's first, second, and third laws. Don't forget, these notes are posted on YouTube under Jerm Moser Productions. Please subscribe and follow for all your notes and other fun stuff we do in class. Have a great Wednesday, and later.